let's talk about truth tables. So a truth table is a table which sets out all the possible truth values that a compound statement can take. I know that's a lot to process, but the idea is that we start with two statements. So let P and Q be statements. Two statements like so. So for instance, P could be the statement x is greater than 2. Now that statement can be true or false, and that depends on the value that x takes. If x is equal to 4, then P is true, but if x is equal to 1, then P is false. Now that's just a side example. Let's get rid of that. What we're going to do here is we're going to write out a table of all the possible truth values that P and Q could take simultaneously. So P could be true and Q could be true at the same time. We could have true and false. We could have false and true, and then false and false. So those are all the possible truth values that P and Q could take simultaneously. Now, if we combine those two statements with a connective, so let's say P or Q, the truth values that P or Q will take will depend on the truth values that P and Q will take individually. Now the rule here is that P or Q is true if at least one of the two P or Q is true. So this means we have true and true. This is going to yield true. We have true and false. So that is true. We have false and true. That is true because in those two cases we have at least one true. But at last we have false and false. We need at least one, so this is going to be false. Now for P and Q, we need both P and Q to be true at the same time. So we have true and true, that is true, but then we have a false, false, and false, false. So those are all going to be false. Okay, because we need P and Q to be true at the same time for this compound statement to be true. Now, what about implication? P implies Q. Now, the idea here is that if we start from something that is true, then it is possible to imply something that is true. However, it's not possible to start from something that is true, so a statement that is true, and imply something that is false. So the implication here is going to be false. So you can't start from something that is true and imply that 1 is equal to 0. Okay, so you cannot do something like that. On the other hand, you can start from falsehoods and imply anything that you want. Okay, so we have true and true here. Let me give you an example. You've probably seen on the internet some supposed proofs that 1 is equal to 0, and that is from starting from a falsehood. So you start from a falsehood and you can imply something that is false. Usually it's something like a division by 0, which you're not allowed to do. Now, that doesn't mean that the implication is true that you want to do this. This is really bad. Do not start from a falsehood. This is how you end up with bad results, like concluding that 1 is equal to 0. Now, what about P is equivalent to Q? Now, in this case, the equivalence is going to be true when both of the statements P and Q have the same truth value. So we have true and true. This is going to be true. We have true and false, false and true. In this case, they're different. So we have false, false, and then false and false. They're both the same, so this is true. Now, another one that I want to show you is the negation. So we have P. P can be true or false. Now the negation of P simply switches the truth values of P. So we would have false and true like so. Truth tables are really interesting in that they can help us determine when two statements essentially mean the same thing. So let's have an example here. Let's start again with P and Q. So we have true, true, false, and false. And here we have true, false, true, false. Now, if I negate P here, I'm going to have false, false, true, and true. And if I take not P or Q, So remember here, we need at least not P to be true or Q to be true. So between these two, we have one true. On the second line, they're both false, so the OR is false. Then we have true, true. That's going to be true. And false, true. That's going to be true as well. Now notice that P implies Q has the same truth table. We've written it above here. It's true, false, true, true. Okay, so we have true, false, true, true, like so. So we have the same truth table. And this means that with respect to their truth values, those two statements mean the same thing. So let's write an example with this actual statements. Let's say P is the statement, the function f is differentiable. You don't need to know what a function is. You don't need to know what differentiable means. So Q could be the function f is continuous. So the function f is continuous. Now, it is actually true that P implies Q. So a function that is differentiable is necessarily continuous. So P implies Q is if the function f is differentiable. If it is differentiable, my God, this is long to write, then it is continuous. So it is continuous like so. Now saying if the function is differentiable, then it is continuous holds the same truth value. So it's basically saying the same thing as not P or Q. So the negation of P is the function f is not differentiable. The function f is not differentiable, or, so we have the or here, it is continuous. And if you spend a sufficient amount of time thinking about this, even in everyday language, this should make sense to you. Now, I'm going to leave you with an exercise, but we're going to go through many more examples like this. So the exercise is, so let me write that exercise. The exercise is show that P is equivalent to Q and P implies Q and Q implies P have the same truth table. Okay, so the idea is that you're going to start with P and then P and Q, so write out all the possible combinations. Then you write the column for P implies Q, and then the column for Q implies P. Do the same for P implies Q and Q implies P, and finish with P is equivalent to Q. And you're going to want to compare those two columns, just like we did right here. But as for now, I'll leave it at that. Take it easy and enjoy yourselves.